Distinguishable and indistinguishable particle in statistical mechanics. Today our topic is about distinguished and indistinguished particle. This topic is also studied in advanced statistical mechanics and in statistical thermodynamics, and third is statistical mechanics. In three categories the topic is same. What are the distinguishable particle? Then we will know about the history of distinguishable particle, and third we see the classical theory of distinguishable particle, and then we study about what are indistinguishable particles and indistinguishable particles in quantum mechanics, and further we will study about the fermionic system of two particles and then study the boson system of two particles. We will study all these topics step by step in this lecture. So if you have a question, then you will leave your comment in comment section below. What is distinguishable particle? Before starting the lecture, in simple words, if I tell you that what are the distinguishable particle, for example, if you have two colors, one is the black and other is the yellow, you can easily differentiate or distinguish between these two colors. So in same term, we define the distinguishable particles. Distinguishable particles are those that have unique properties such as position, momentum or internal state. So here in term of particle or system of particle, you can easily distinguish between the particle if you know about their position or momentum or internal state. You can always identify which one is which. So already I have tell you with a simple example that if you have black color and yellow color, you can easily tell which one is which. In simple example we see, imagine two marble of different colors. You can easily distinguish between these based on their color. For example, these are the two colors, one is the black and other is the yellow. You can easily distinguish between these two colors. On the other hand, if you have two particles, their wave function is also given here, but you can't distinguish them because they are totally identical, their particle size is same, so you can't distinguish between them. So they are non-distinguished or indistinguishable particle. But on the other hand, right side diagram shows you that they are distinguishable particle. So before starting the distinguishable particle, we go back into the history and study about the scientists who gave their ideas about distinguishable particle. There are two types of ideas. One is the classical ideas and other is the quantum mechanical ideas or quantum ideas. In quantum mechanics we study different latest ideas. So in classical ideas we see scientists Maxwell, Boltzmann and Gibbs who gave their ideas in statistical mechanics. So further we move in the history and see that they are also called classical particles. As you can see here the diagram. So if we take, these are the particles, black and yellow, they are the classical particles and easily can be distinguished, and they don't follow Heisenberg uncertainty principle, because in Heisenberg uncertainty principle we know exact about the position or momentum but not both. We know only one of them, only we know that the position of a particle or momentum of a particle. We study objects macrocally but not microcally. So here is the diagram that show the identical or indistinguishable particle because we can't differentiate them, they are totally look like the same. If we see in the classical theory, all the particles we see or observe, they are classically same, but quantum mechanically they are not same. That's why they don't follow Heisenberg uncertainty principle. Here we will study about the classical key points of distinguishable particle. One of them is they obey Maxwell-Boltzmann statistics, and other one is that in classical mechanics all particles are considered distinguishable, and third one is that we can trace movement of particle through their trajectory, and next is we can also call the localized particle, mean we can detect their energy or position or momentum, we can detect. And next, for a two particle system, the total wave function of system can be written as in this wave function sign is one is the one particle and two is the second particle, and the wave function of first particle and then wave function of second particle, and we see these particles in detail further in boson and fermion. Here is the only formula we see here, and further we see in detail. In same sense, we have two particles whose wave is generated due to their movement, and wave function can be determined by this formulation. Further, if we go in detail to study classical theory of distinguishable particle, here you can see the particle, these are the electron. You can easily distinguish between them. They looks like identical and we can easily distinguish them. So the statement is, if we have collection of electrons, are they distinguishable? So this is the question. So the answer is, this can be distinguishable because we can differentiate between them easily because they are separate. If we localize particle, we can say system of identical and distinguishable particles. So this is the system of three particles and only three particles are the electron. We can easily distinguish between them, but they are identical because their size is same, so they are identical. If we trace the individual particle in system, then it will be the system of identical and distinguishable particle. So here there is the two conditions which are summarized. So the first condition is particle are identical, and second condition is distinguishable particle because we can easily differentiate between them that which particle is which one. So here these two conditions are summarized. This was the classical nature of distinguishable particle. Before studying quantum mechanically nature of distinguishable particle, we study about the indistinguishable particle and then move to the quantum mechanical nature of particles. So question is, what are indistinguishable particle? In simple term, particle having overlapped wave function are called indistinguishable particle. Here you can see about two particles whose color is same. So they are indistinguishable particle. We can't differentiate between them because they are totally same. Their wave function is totally same. So the example is, if you have two electrons in the same energy state, they have the same properties because of indistinguishable particle. That example is given below. If we go further in detail of indistinguishable particles are the particles that are identical, means same in all relevant properties, making it impossible to tell them apart from one another. Indistinguished particle have same spin, energy level and other intrinsic properties like electron, proton and photon. So in simple terms, if you have two boxes of same color, mean two boxes, two color and their color is black, so they are the totally same. Their energy, their color, all the things are same. In same term, indistinguishable particle have all the things very same. Particle, their spin, their energy level, their intrinsic means internal properties like electron, proton and photon, all the properties would be the same. For example, if you have two electrons in same energy state, there is no way to determine which electron is which since they have the same properties. In another important point, we understand, don't judge symbol by wording distinguishable and indistinguishable. Look at the energy of individual particle. If it is discrete, then particle will be quantum, otherwise classical. So these were the two major important points between classical and quantum mechanics. If we move toward quantum statistical history, we see the scientists who worked on particle or system of a particle. We see about these scientists. One of them is Bose-Einstein statistics. There is the two scientists, one is the Boson and other is the Einstein. These two scientists who worked on the particle and gave their ideas about the particle or system of particle, they are collectively called Bose-Einstein statistics. And second one is the Fermi-Dirac statistics. There are the two scientists, one is the Fermi and other one is the Dirac scientist, who work on statistical particles and study about the system of particle and tells us about the different theories in distinguished and indistinguishable particle. So their theory is known as Fermi-Dirac. Bose-Einstein statistic, particles having integer spin and photons, and in Fermi-Dirac statistic, particle having odd integral spin and electron. We have already studied about the spin nature. You can see the lecture and whose link is given in the description. You can easily study about their spin, or what is the spin nature and how we can determine the spin nature. We have already studied in detail. We move further. They are also called quantum particle. That's why they follow quantum statistics. They will obey Heisenberg uncertainty. These are the properties which we study in quantum statistical history. They will obey Heisenberg uncertainty principle, means they study about the position and momentum of a particle. Further, you can't determine position and momentum precisely at the same time. So this was the basic term which understand in Heisenberg uncertainty, that we can't determine the position and momentum simultaneously. So if we see, they are also called non-localized particles. Non-localized particle means particle that do not have definite position or momenta. This means that we can't understand about the position and momenta at the same time. That's the same term which we understand in Heisenberg uncertainty principle. If we see further conclusion, we can't trace individual particle. So in quantum statistical mechanics, we can't trace individual particle, and indistinguishability is seen for identical particle. So these are the basic consequences which we study in quantum statistical mechanics. Further, we will move to study indistinguishable particle in quantum mechanics. So indistinguishable particle in quantum mechanically, we have already seen. First one was the Bose-Einstein statistic, in which we study particle having integer spin and photons, and second one was the Fermi-Dirac statistic, in which we study about the odd integral spin and electron. And further, if we see total wave function for fermionic system, anti-symmetric with respect to exchange of particles. For example, if we have wave function of two particles, one is spin and other is the special. Consider two particles whose wave function can be represented by this symbol named as psi. So the total wave function can be determined by the spin up and spin down, and we will add them and get their final result. We can also represent the total wave function of indistinguishable particle by two terms. One is spin and other is the special wave function. So the question is, what is special wave function? So special wave function is discrete. This means that their spin can either be plus 1 by 2 or minus 1 by 2. We can take it spin up or spin down motion term. So the special wave function denoted by symbol psi, and in three coordinate x, y, z for three particle or a system of particle, in which we are studying about the three particle system, or simply by psi into r. It is mathematical function that describes the behavior of quantum system, such as particle position in three-dimensional space, is discrete. So the special function is clear now. So now we will move to next, which is spin wave function, which is continuous. This means that the spin of a quantum particle can take on any value within a continuous range. To study distinguishable and indistinguishable particle quantum mechanically, first of all we will need to study about the fermionic system of two particles. So in simple term, fermionic system of two particles are a group of subatomic particles having odd integral angular momentum. Spin value is 1 by 2, 3 by 2, 5 by 2 and up to so on. So in simple term, there are n distinguishable harmonic oscillator. They are oscillating quantum mechanically. Now we will take a wave function of this motion, this oscillatory motion of a particle. So they can be written as E is the energy, n number of particle, half h cut omega, where n is the principal quantum number and h cut omega represent the energy spacing between adjacent energy level. So in Fermi-Dirac statistics, particles that follow Fermi-Dirac statistics are also indistinguishable, but have a restriction that only one particle can occupy a particular quantum state at a time. These particles are called fermions, and example include electron, proton and neutron. All these things we already have studied and reviewed about the history of quantum mechanically and classical theories of particle or a system of particles. So this is about only fermionic system of two particles. Distinguishable harmonic oscillator, they are oscillating quantum statistically. So their wave function can be represented quantum mechanically here. So one is the first particle, two is the second particle, and this is the total wave function. So here we use formulation of, and psi A is the first particle wave function and psi B is the second particle distribution, and here we are studying about the probability. So this is the second particle and this is the first particle. Psi B is the wave function of first particle. So we exchange their position. So if we exchange the position of a particle, then if we see that if we have second particle first and first particle in second position, then their wave function will also change. So here you can see we take a wave function of first particle, but here first particle is 2, so we take second particle and then take first particle, and here we take first of all second particle, and here we take only first particle wave function and then second. So we have only exchange position of these particles. If we move further, so the total momentum, total wave function will be with the negative sign. This negative sign is further explained that we have changed their position. This means that first of all, if we take second particle and then first particle, here we take first particle and then second particle, we exchange their position, so their wave function position also change and their value will also change. So it means total wave function is anti-symmetric in character under particle exchange for fermion. So this was the result of fermionic system of two particles. Next, in boson system of two particles, we see that they show symmetric nature is represented. First of all, we know about the symmetric under particular wave function. Consider particle that follow Bose-Einstein statistics are indistinguishable and can occupy the same quantum state simultaneously. So they are identical particles. Also, these particles are called bosons, and example include photon, particle of light, gluons, and some atomic nuclei. In simple word, boson system of particle only study indistinguishable particle and tells us about the symmetric nature of particles. Nature of bosons system of two particle would take symmetric under particular wave function. So the wave function is given here and we will prove that boson system has symmetric nature. So at the same time earlier as we see about the two particle in fermion, here we will also study about the two particle in boson. First wave function is 1 and second particle wave function is represented by 2. So in same sense we have only here plus sign. At that position in fermion we was taken a negative sign, but here we take only plus sign. So in same sense when we exchange the particle position, so negative sign will occur, but this will not change the value and prove the symmetric nature. Here you can see the result when we take or when we exchange the position of a particle and exchange their position, first take second and then take first, and here first we take first particle and then second, but here we take only second particle first. By putting values we did not change our value, so this shows that it means total wave function is symmetric in character under particular exchange for boson. So in boson we study only identical particle. Due to identical nature of particle, they have same value. Next are the important questions which are given here. If you understand this topic correctly, then answer your questions below in comment section. The first question is, how do we determine whether particles are distinguishable? What are the implications of particle indistinguishability? How does the concept of indistinguishable particle relate to quantum statistics? And can you provide example of indistinguishable particle in real world system? And in last, how does the behavior of distinguishable particle differ from that of distinguishable particle in quantum system? If you have any question, you can leave your question in comment section below.